The impulse momentum theorem says that the impulse due to a single force on an object equals the resulting momentum change in the absence of other forces. In other words, I is equal to delta P. Show that this is true. I've stated that very carefully here because usually the impulse momentum theorem is stated for just one force. One could argue, though, like, well, what if that one force really is equivalent to like the net force of a bunch of forces acting? Would it still apply? My answer would be yes, but anyway, it's not always stated that way. So I'm keeping things simple, so we keep kind of our picture simple for this as we look into it. Since it's saying to show this thing, we need to start with something that we already know. If there's a single force acting on a system, what we showed earlier in this chapter, based on Newton's second law, we showed that the net force is equal to the change in momentum over whatever amount of time it took for that change, which we've interpreted as a time rate of change of momentum. So I'm taking this as a starting point, as kind of a statement of Newton's second law that we showed in this chapter is also equivalent to the F equals ma that we usually use, statement of Newton's second law. I'm just going to do a really simple algebra maneuver here and say, okay, let me do it over here, leave a little space. I'm going to multiply both sides of this equation by delta t. So if I do that on one side, I get force times delta t. This always feels a little weird, putting force vector times delta t. At least it does to me, because putting a vector in front of a scalar seems weird, but it's going to make sense physically, I think. It might not seem weird to you, though, so anyways. But is equal to change in momentum. Well, guess what? We have it, because the definition of impulse was force times time, right? This is force times time. We saw that technically this was average force, but I think in this example, we could maybe assume that either this is an average force or that it was a constant force, in which case the average force and the force itself are equal to each other. But what I'm suggesting here is, since this is the definition of impulse, we have arrived at that result of impulse is equal to change in momentum, which again is that statement of the impulse momentum theorem. So in that sense, as a theorem, it's really not that big a deal, because all we had to do, as it says here, is multiply both sides by time, and all of a sudden you have a different way of looking at things.